Bismillahirrahmanirrahim. Assalamu alaikum students. Today's topic is going to be about AC generator, where AC means alternating current generator. Now, how can we produce electricity? This is a device by which we can produce a current. We have learned that when a current carrying coil is placed in a magnetic field like this, let's say assume that this is a magnetic field where this is the north pole and this is the south pole, and when we place a coil inside it like this, it tends to rotate basically when the current is basically passing through it. It tends to rotate. But what if we are rotating the coil itself in the clockwise direction or in the anti-clockwise direction? What will happen then? A torque acts on it and rotates the coil. What happens if the coil of the wire is rotated in the magnetic field? That means if we applying the magnetic field over here in the clockwise direction, right over here, or in, we can say, in other words, we can also move in the anti-clockwise direction. What will happen then? Can a current be produced in the coil? Yes, it does. That when we basically move this coil inside a magnetic field, there will be a current produced inside it. Such a device is known as current generator. So the simple definition of current generator is a current generator is a device which converts the mechanical energy into electrical energy. So a simple device basically which converts the mechanical energy into electrical energy. That device is known as AC generator. Keeping that in our mind, what is the principle? The principle of electrical generator is based on Faraday's law. Now, what was Faraday's law? Actually, whenever the magnetic field basically changes due to some movement of a rod inside it, it will produce a current or EMF in that. So we can represent it very simply with the help of a formula, which is E is equal to delta phi over delta T. That means the flux, whenever the magnetic flux is changed, that field is changed due to any reason, due to any wind, you can say it is because of water or any other device which basically rotates it with respect to time, it will produce an EMF and which later on produce electricity. So he says on base of Faraday's law, the electromagnetic induction, when the coil is rotated in the magnetic field by some mechanical means, the magnetic flux through the coil changes. That means there's a change in the magnetic flux. And consequently, EMF is produced in the coil. And that means some EMF will be produced in that coil. Keeping that in our mind, if a generator is connected to an external circuit, that means if we connect this EMF to external source, let's say over here, a bulb basically is connected to this external source, it will light up because it is giving off electricity. An electric current is the output of the generator. Let the rectangular loop of wire A be placed in a uniform magnetic field B. So let us represent this whole thing in the form of diagram. So here is a wire, let's call it A, and in a magnetic field over here, just B. Now, in this case, as we can see very clearly, that we are naming the coil as over here, as this point, let's call it A, let's call this point B, let's call this point C, and this point D. We see that the coil basically tends to rotate whenever it rotates due to some mechanical means. Let's rotate it in the z-axis in the anti-clockwise direction. And we see that it is in a magnetic field, and the magnetic field, we can see that it is moving from north to south. Now, because of this reason, we can use the right-hand rule in this case, and we can see if we put the finger, the index finger along the magnetic field, which is B, and the you can say the current basically flows in the upward direction. Let's say the magnetic is basically facing upwards, and the motion of that body will be into the page. So in that case, we'll show the thumb in this direction. So this is our movement of the, you can say the current in this case. Now in this case, we are showing that magnetic field is in certain direction. Let's say over here, the movement of the charge is over here. That's represented by V. And in this case, the motion or force of the body will be into the page like over here. So instead of drawing a finger, basically, we can show it like this. So the charge basically move the body into the page. So it rotates in this direction. The force will be applied over here. And the EMF basically is applied on this rod, which is equal to, let's call this EMF from A to B. It will be V, B, L sine theta. So if theta is 90 degree, because it is the angle between the length and the magnetic field, so they both are 90 degrees to each other. As you can see over here, length is over here and the angle is 90. The velocity is also perpendicular. So if sine 90 is there, so we can say EB is equal to VEL sine theta, or sine theta, which we already know basically is equal to 1. And the same way, the current basically flows through here, and in this direction goes back to this point and basically out of this direction. So let's draw something else over here, which is required, which connects to the external circuit. There are carbon brushes over here as well. And these carbon brushes are connected to the external source. And that external source can be anything. It can be a bulb. Let's draw a bulb over here, which lights up when the current passes through it. So here's the scenario for us. So in this case, let's see what else we can basically induce into this whole scenario. Now, in this case, a loop is rotated about the z-axis to its center at a constant angular velocity, which is omega. That this loop basically rotates in the anti-clockwise direction with the help of some external force. Let's call it wind, let's call it water, whatever you want. One end of the loop attached to the metal rings R and the other end to the rings R dash. Let's call this R and the other one is R dash. These rings are called slip rings and are concentric to the axis of loop rotation with it. These two rings, that means R and R dash, both combined are known as slip rings. I'll write that again. Slip rings. And these rings basically rotate with as the coil rotates as well. And basically they are touching the carbon fibers, or you can say carbon brushes over here, so that the current basically is given onto the external circuit. The rings R and R dash are sliding against the stationary carbon brushes. So here are the carbon brushes. Which basically supply the current to the external source. Let's mention the direction of the current as well over here. So in this case, the current is flowing in this direction. That means, let me draw it with the red color so it is quite easy for everyone to see. So the current goes from here, over here, and the anti-clockwise direction goes down and ends up over here. So whole circuit basically is completed in this case. Now, is to which an external circuit is connected. To calculate the induced EMF in the loop, consider a position figure while is rotating anti-clockwise. Now, this whole coil is rotating in the anti-clockwise direction. The figure shows the top view of the coil. Let's say over here, if we see this only view, then this point is A, this point is D. And this is North Pole and this is South Pole. So it has to basically rotate in the anti-clockwise direction. The vertical side AB of the loop is moving with the velocity V with the magnetic field with the angle V and B is theta. That means the angle between the velocity, which is over here, which is the velocity, and the magnetic field, which is over here, the angle is basically, we're calling it theta. The motional EMF in the side A, B has the magnitude. Now let's see that how this whole thing basically rotates. Let me clear this out so that it is clear. So this coil will rotate over here, and this coil will rotate over here, and it will keep on rotating. And you can see the slip rings basically rotating with them as well, like this. So as you can see over here, it is rotating about its z-axis right over here, right at the center point. So it is rotating in the omega angular velocity form. Just very clear now. If we basically increase the magnetic field or we increase the motion of the movement of the coil, like over here, so it will basically rotate much faster and we get more and more current in this way. Now we were talking about the motional EMF along the side AB, which was motional EMF, which was equal to VBL sine theta. In the same way, the direction of the induced current in the wire AB is same as that of the force experienced by the charge in the wire from top to bottom. In the other case, while it was rotating around, the same amount of EMF is induced in the side CD, but the direction of the current was going in the bottom direction. That means now in this case, we can say one side was moving in upper direction, the other side, it was moving in the downward direction. And then this whole cycle basically reversed. Now, keeping that in mind, we can say now that CD is equal to, EMF of CD is equal to VBL sine theta. So both of them basically are producing the EMF. But what about the top and the bottom part? So for that, the top part basically does not play any important part in the EMF. It is negligible. And the bottom part of this coil also does not play any important part in the movement of this coil. Only these two parts on the sides of the coil basically are making the coil rotate. Now, in this case, the net contribution of EMF of side BC and DA is 0 because the force acting on the charges inside BC and AD are not along the wire. And that is why they are not producing any force to rotate it. So the EMF along BC and DA are equal to 0. Since both EMF of the side AB and CD drive the current in the same direction around the loop, the total EMF in the loop is, that means we are adding them up. So the total EMF, you can see over here, the total EMF is equal to E, that is the total EMF of AB plus ECD, which is total EMF of CD. So the total EMF produced by the coil will be equal to E, which is the EMF is equal to VBL sine theta plus VBL sine theta, because both of them, as you can see over here, are being added up to get the value of the total EMF produced by the coil. So we get EMF is equal to 2VBL sine theta. If the loop is replaced by the number of turns, the total number EMF in the coil will be n times, of course. So we'll basically introduce a new number because the number of coil, let's say it was one coil only over here. Now, if we introduce another coil in the same way, so the EMF will be basically obviously increase n number of times. So EMF is equal to 2 VBL sine theta. So in the linear speed of vertical wire is related to the angular speed because it was moving in the angular velocity omega. So we have to represent this speed, which is represented by V over here, in the angular form. So how can we do that? We know that V is equal to R omega or omega R. So let's put in this value in this V over here. We get where R is the distance of vertical wire from the center of the coil, substituting the value of omega for V. So it is r omega for V. So what do we get? We get E is equal to 2 n r omega. Basically, instead of this V, we're putting r omega VBL sine theta. So we can represent it in a different way. E is equal to omega 2 RLB sine theta. So the length was over here from was L, and the radius, as you can see from here to here, is R. So R plus R is equal to 2R over here. So if we multiply this 2R and we multiply it with the length L, which is over here, so we have the whole area of this coil. So instead of writing down this 2RL, we are writing down A, which is the area of that coil right over here. Keeping that in our mind, we have now EMF is equal to n omega AB sine theta, where A is equal to 2RL, which is the area of the coil. As the angular displacement, theta is equal to omega t. So equation becomes E is equal to n omega AB sine omega t. Now, this is the value for the angular velocity for that coil. Now, equation shows that induced EMF varies sinusoidally with E naught times when the sine omega t is equal to 1. When this sine omega t has the angle which is equal to 90 degrees, basically, which are making 90 degree with each other. So the maximum value we will get is 1. So that is why if we replace this as 1 at the angle of 90, what do we get? We get maximum value of EMF, which is E naught is equal to n omega AB. If we replace this E naught with this n omega AB in the first equation right over here, what do we get? We get E is equal to E naught sine omega t. Keeping that in our minds, that E is equal to E omega, E naught, which is the maximum EMF which we can get of this whole situation, and sine omega t. This is the relationship at any condition, any instant of the coil. Now there's an alternate method of this whole scenario, which is basically we have the flux, which depends upon the magnetic field and the area of the coil and the number of turns of that coil as well. And because it is a dot product between B and A, so we can say it is BA cos theta, where B is the magnetic field, you can say, and A is the area. Now, in this case, if we are to convert this in the form of omega t, that means we know that theta is equal to omega t, as we can show over here. So NAB, which is equal to flux, is equal to cos omega t. So induce EMF. Now there's no EMF mentioned over here, but we remember the Faraday's law, which was equal to E is equal to delta phi divided by delta t, and there's a negative sign over here. Now in this case, we are saying that the EMF, which is negative sign into delta phi or delta t, that means change of flux with respect to time. Instead of this phi, they're putting the value of phi in this equation. So it is delta divided by delta t into NAB cos omega t. Now let us apply some calculus over here. So in this case, all of these values are constant. The number of turns is also constant. The area is also constant throughout the process. And the magnetic field is also constant throughout the process. But we are limiting the cos omega t over here, and we are dividing it by delta t. So limit approaches to 0, delta cos omega t divided by t. So we are basically differentiating the cos omega t over here. So if we differentiate, what do we get? So if we differentiate or we limitize the delta t approaches 0, delta cos omega t divided by t, it will be equal to minus omega sine omega t. That means this omega is constant value. It will come to the first part, and cos will be converted into sine. Now the new concept will be this negative sign. Basically, we go over here and basically multiply with this negative sign, it will be plus. So EMF will be equal to NAB omega sine omega t. And for maximum value, again, the sine omega t will be equal to 1 because sine omega t, if it is equal to sine 90 degree, so it will be equal to 1. So it will have a maximum value of EMF max, which is n omega AP. So replacing this whole thing with the help of E max, what do we get? We get simple version. Hence, the induced EMF for any instant of time, we get that E is equal to E max or E naught sine omega t. So in both the methods, we get the same answer, that E is equal to E max sine omega t. Or we can say instead of omega, where omega is equal to 2 pi over t, which is a time period for a whole rotation of the coil, and which can also be represented as omega f, because we know that time period is inversely proportional to the frequency. So instead of writing like that, we can say E is equal to E max sine 2 pi ft. Now we were talking about current, not EMF. So if R is the resistance of the coil, then by Ohm's law, the induced current in the coil will be, as we remember Ohm's law, which is equal to V is equal to IR. So to find the value of I, so we can divide V by R. So we have the formula already over here. So we are dividing it by R. So I will be equal to EMF divided by R is equal to E naught sine omega t divided by R. So this will be equal to I naught, and this will be equal to I. So I will be equal to I naught sine omega t, or we can say simply I is equal to I naught sine theta, we can simply say. So here we go. So I is equal to I naught sine omega t, where I naught is the maximum current. The angular speed omega of the coil is related to the frequency of rotation, which is 2 pi f. Equation indicates the variation of current as a function of theta is equal to 2 pi f. So instead of writing like that, the figure shows, we can say that this whole thing can be written as I is equal to I naught sine 2 pi f t. Figure shows the graph of the current corresponding to different position of the loop. Let's show the different condition of the loop over here. So here is the graph with respect to time over here. Time is on the x-axis, and this is zero current, and this is the maximum current, which is represented by I naught over here. So in this case, we divide the whole scenario into 4 intervals, between which we'll see that how the coil was behaving. First of all, the time was 0. Then we'll see that how the current behaved at that point. Then the time was t by 4, that quarter of the time passed. Then we'll see that it is t by 2, half of the time which is passing. And then it is 3t by 4, and the whole time period, which is t. And this whole coil basically rotates in this whole time period. So let's see how the whole coil basically rotates in this whole time period. Let me write down the E naught so that it is clear. It is the maximum value of current which we get in certain amount of time. This is E naught, maximum current. So here is the situation again, and here's the coil in this scenario, that the top of the coil, A part is over here and D part is over here, and inside the magnetic field basically is moving from north to south over here. Now, where theta was basically the angle between the velocity of that coil and the magnetic field. So here we are going to represent the velocity in this case over here, and the magnetic field is also in the same direction. Let me differentiate the colors over here. The magnetic field basically I'm going to show with the red color, like over here, and the velocity I'm going to show with the blue color, so over here. So what is the angle between these two arrows over here? So these arrows basically are showing the angle between them is 0, because both of them are in the same direction. When the angle between V and B is 0, the plane of the loop is perpendicular to the magnetic field, and the current is 0 over here. The current is 0, so we'll put the current over here at 0. So at 0 time, the time was 0. The time over here is t by 4. Again, the time over here is t by 2, 3t by 2, and you can say over here 3t by 4, and over here it is t. So over here, the angle is 0 and the current is 0. Maximum current is basically placed over here. This is represented by I naught. So here we go. As it moves, now as you can see, the velocity has changed its direction. Now it is in the upper direction, but the magnetic field has not. It is basically moving same as to the north to south. So as the theta increases, the current also increases, and theta, which is equal to 90 degree, and the loop is parallel to the magnetic field. The current is maximum and directing along the side A, B, C, D, A. Now the current basically in this case has risen up from 0 to its maximum value at this point. So over here, its value will be maximum. If we put in the values over here as well, so if I is equal to I naught sine, you can say over here 90 degrees, because the theta was equal to 90, because this whole thing can be written as I naught sine theta. So if we put the value of theta is equal to 90, then sine 90 is equal to 1, and I at this instant will be equal to I naught. And that is what exactly is going around over here. Now, keeping that in our minds, let's continue. And coil keeps on rotating in this case as well. And now the velocity is in anti-clockwise direction, but the magnetic field is again in the same direction, like over here from north to south. So these two angles is making an angle of 180 degree over here. On further increase in the theta, the decrease and angle 180, the radian, pi radian, the current becomes 0, and the loop again perpendicular to B from 180 to 270, the current decreases, but in reverse direction, and it's clear from the figure, the current will now directed from along DCBAD. Now in this case, we can see clearly, now the current has decreased from this point to 0, and it's going down now. It's the next step, it will go underneath the 0 point as well. As we continue, we'll see that as it moves along, now in the case of 270, the velocity over here is in the downward direction, right over here. And the magnetic field is again in the same direction, which is north to south. Now this angle is basically making an angle of 270, which is 3 pi by 2 or 3t by 4 at this point. Radian, the current is maximum in the reverse direction as the loop is parallel to B. Loop is being parallel to B, which is along the magnetic field lines. So let's draw the curved line over here. So it goes down like this. And in the same way at the last point as well, it keeps on rotating and completes the whole cycle over here. So magnetic field is along the same point, which is it was before. The velocity is in the same direction as that of the magnetic field. So here we can see that angle again is 360, or you can say 0 degree again. So at 360 or 2 pi radian, one rotation is complete. The loop is perpendicular to B, and the current decreases to 0. After one rotation, the cycle repeats itself. The current alternates, and once the cycle is complete, therefore the current is called alternating, and the reverse direction times per second. That means now in this case, we can clearly see that the current basically goes back to its original point as it was starting. So as you can see over here, as you can see this line, it is sometimes positive, sometimes it is negative, and it goes on. So that is why it is known as alternating current. Now we can represent this whole thing in the form of clear graph. As you can see over here, it is a very clear line. Sometimes it is positive, sometimes it's negative. In actual practice, the number of coils are wound around the iron cylinder, which it rotates in the magnetic field. This assembly is called armature. The magnetic field is usually provided by electromagnets. The armature is rotated by a fuel engine or turbine run by waterfall. In some commercial generators, the field magnetic field rotates around the stationary armature. Now, what is he saying actually in this case? that if we place an iron cylinder inside this coil so that it rotates quite well as compared to before, instead of simply just rotating this only coil and produce a very lower amount of current. In actual practice, the number of coil wound around the iron cylinder, which is rotated in the magnetic field, the assembly is called an armature. The magnetic field is usually provided by electromagnet. The armature is rotated by the fuel engine or turbine by a waterfall. In some commercial generators, the magnetic field is rotated around a stationary armature. That means if we introduce this iron cylinder over here, so it is very easy for us to rotate this whole coil and generate more and more electricity. And because of that reason, this bulb over here will light up more and more. And we can basically generate more electricity so we can give to the whole world. I enjoyed today's lecture. I hope you enjoyed it too. Inshallah, we'll meet again. Until then, Allah Hafiz. Bye-bye.